I'll begin today, this week's set of lectures. So we'll essentially do a small review of what we have done so far. And then we'll also discuss some aspects of how to test the linear relationship of the model that we have placed. Okay. So let me just recall what we've been doing so far. So we've been working with predominantly linear models. So we have a data set Y. We have a model X beta, which is the x value of Y given x value of Y. And this is like an error which is assumed to be uncorrelated, but variance sigma square. That's the equivalent of this, or we could, the same way, this is what we've been calling in short a linear model. One could also think, it's also like, we also understood it looking like each yi looks like beta naught plus beta 1 x1 plus beta n x beta m xm and plus epsilon I, and we have 1 less than equal to I less than equal to little n, and and we won't estimate the parameter beta, and we assume that each epsilon I was uncorrelated random variables with variance sigma squared, mean zero, and variance sigma squared. Very good. So this is what we're doing, and then last time we discussed this idea of what's called a least squared estimators. And we said that's the one that minimizes the distance between the residual sum of squares, so y minus x naught beta squared. So let me just go back to what last week we did. So we considered this model, and then we said this was the least squared estimate. So we copied it down. So a random vector beta hat is called least squared estimate if it minimizes this. It's back here. This is what we call the least squared estimate. And the way we solve for beta hat, we did it by solving the normal equations, which is what this theorem gave us. This theorem gave us that the least squared estimate on any linear model would be solved, the least squared estimate would solve this equation, which we call it the normal equation. And these were called the normal equations. Okay, so today what I'm going to do is I'll begin with a simple example, so that we sort of we didn't do any examples last 2 weeks in some sense. The homework had examples, but so what we'll do is we'll start a bunch of examples, and then I'd like to develop some statistical questions, like I'd like to examine, is this linear model really valid or not? So how do I statistically test for that? Is there an easy way to sort of provide a hypothesis if these coefficients are really non-zero or zero in some sense, and understand the effect of the variable x1 on the variable y. So now, today, let me just start with an example. Suppose we're given the data. Let's say it's a very simple one variable data. Let's say so. The data set is just let's say x and y. Let's call it y here, x here, and then y here. X is, let's say, a very simple one, 2, and Y is 1, and X is 3 halves, Y was, let's say, 2, and when X is, let's say, 4, let's say 4, Y, let's say 1. This is the data set that I have, okay? So clearly, of course, I don't know how to make sense of a line because it goes up and comes down. It's a 3-point data set in a very simple way. And I think of a, let's say I want to fit a linear model. Well, let's say, and here this is only Y is equal to beta naught plus beta 1 X plus 11 epsilon r. This is what the linear model looks like. Epsilon is there, right? Is there. So now, if I want to do a least, let's just do a least square estimate. So what does least square estimate look like? So the x vector will look like in the linear model will look like 1, 3, 1, right? 1, 1, 1, and the second column will be 2, 3 halves, and 4. That's x, and your y vector would look like 1, 2, 1, and that's y vector look like. And you want to find the least square estimate, right? And the beta vector looks like beta naught, beta 1. So how do you do it? So we want to find the least square estimate, so we would go and solve this equation: x transpose x times beta is equal to x transpose 1. Let's try and do that. So how does it work now? So first thing we'll have to do is we have to find. So let's try and find the least square estimate. So how does one do that? So you need to solve. We need to solve x transpose x. So we need to solve x transpose x. Beta is equal to x transpose 1. If we solve this, then we know how to get the equation. So let's try. What is x transpose x? So now x transpose x is equal to, x transpose is what looks like what now? It has 2 rows, so it's 1, 1, 1, right? That's the first row. The bottom row looks like 2, 3 halves, and 4, right? And x is the vector 1, 1, 1, 2, 3 halves, and 4. And this, if you do the multiplication, what will you get? The first column you'll get 1 plus 1 plus 1, and that's 3. Right? The second column, what will you get? You get 2 plus 3 halves plus 4. That's 7 by 2, right? 2 plus 4 is 6. 2 plus 4 is 6, and then 6 plus 3 halves is 15 by 2. That's 7.5. You get in this column, you'll get 2 plus 3 halves plus 4. That's 6 plus 3 halves. Again, symmetric matrix, 7.5. And this last row will be 2, 4 plus 4, 16. 16 plus 9 by 4. So that'll give you 89 by. Very good. That's x transpose x. Right? Let's do x transpose y now. So what does x transpose y look like? That's again look like 1, 1, 1, 2, 3 halves, and 4. And 1, what's y? Y is 1, 2, 1. So 1, 2, 1. So what's it going to look like? A little bigger. So that looks like 1 plus 2 plus 1 is 4. That's the first one. This 2 plus 3 halves times 2 is 3. Plus 4 is 2 plus 3, 5 plus 4 is 9. So what it looks like. Very cool. Okay, very nice. So now I have to solve this, right? So how do I solve this now? I have 3. I have 3, 7.5, 7.5, and 89 by 4 times beta naught and beta 1 should be equal to 4 and 9. This is what I have to solve. Very good. So this one can do in many ways. Let's do either the echelon form, or you can solve it in any as exercise linear algebra. Since I will not, I don't want to do this. You can solve for beta naught and beta 1. So I'll let you guys think a little bit. You can solve it. I think you should get beta naught. I have solved it myself in my notes. If I got it correct, beta naught would be equal to, beta naught is equal to, I think, 43 by 21. And beta 1 hat is equal to, I think, minus 2 by 7. That's what I get. Means my least square estimate is of the form 43 by 21 and minus 2 by 7. That's how I complete the calculation of finding the least square estimate for this data set, if I assume a least. So I set up the normal equations, I find x transpose x, and I do this whole thing. Very cool. Today we'll also see in R how to do this, how to set this up properly, and how to use the inbuilt function in a function. So until now, we've been sort of discussing the linear model in sort of a very specific way. And we sort of took a linear model and said, okay, this is where we're going to go with this. And least square estimate gave you a relationship that specified that beta hat looks like this. So let me just do a little bit of a analysis of this. So let's try and discuss some analysis of this before we sort of. So let me call this section as understanding. So it's called understanding. Of course, I'm going to go towards estimating, but understanding or estimating the coefficients. So understanding the estimate of the coefficients. Let's call it as beta hat and beta 1 hat. The first thing you will do is to predict, right? To predict. So what's the first thing we will do? So how do you use beta naught and beta naught typically in this particular model? So let's look at let's do a simple case. Let's call this the simple linear regression. Then we'll do multiple very soon, but let's do simple linear regression. In the simple case, so I have y is equal to beta naught. Each yi is beta naught plus beta 1 x1 plus epsilon xi plus epsilon. Okay. Okay, this is where I was making a small error. Here I should have xi1 and xi1 to xi. That's what I was trying to say. Be careful about. So I have this, and then I want to. This is I estimate beta 1, and I know what beta naught hat is. So a beta naught, I have a least square estimate. Beta naught hat. And beta 1 hat, and they solve. What do? They solve x transpose x times beta naught beta is equal to x transpose 1. Whatever. So if you think a little bit, and here what is the x? Where x was just 1, 1, 1, 1, and 1, and then x1 up to x. And y was just, again, the vector y was y1 up to y. So 1 left. So if you do a little bit of analysis, so linear algebra, so you can calculate what x transpose x. X transpose x would just be, again, 1, 1, 1 all the way, x1, x2, xn all the way, and x is just 1, 1, 1 all the way, and then x1. And this would give you, just do a simple calculation. The first one will be n. The second one will be summation I equal to 1 to n of xi, right? And just make it a little smaller. Copy it, and that will be a symmetric part on this side. Right? Make it smaller, and on this side I'll get a sum of squares. Right? I make those smaller, so it's very cool. So that's what X transpose X looks like, right? And then in this simple regression case, right? And X transpose Y, if you just do a calculation, is just going to be just I'll do the exercise. The first one is just going to be summation I equal to 1 to n of yi, and the bottom is going to be summation I equal to 1 to n of xi y. This is a simple exercise you can try. Right. So now you can just see, let's call this equation 2, let's say. So you can just see solution of equation 2. You can do an explicit calculation. You can do row. You can just do subtract the 2 rows and do this to get beta 1 hat versus beta naught hat is equal to y bar minus beta 1 hat x bar, and beta 1 hat would be just equal to the sum of xy is xi minus x bar minus y minus y bar, the whole thing divided by the 2 sum of squares, right? So sum of squares is going to be summation I equal to 1 to n of xi squared, xi minus x bar, the whole square. Now from this, you can solve, you can just understand exactly. And what is x bar and y bar? X bar is just a sample mean, that is summation of y equal to 1 to n of xi, and y bar is the sample mean. So this is another representation of the solution. So it's a sort of explicit representation of the solution. Very good. So these are the least squared estimates in the simple linear regression case, right? But once you have this, you also have the errors, right? The errors. So what are the errors? Each time, so you have an error because y minus beta, y equal to beta x, beta naught beta on x will not pass through data set. It will miss some points. Right? So there's something called, like we discussed, the RSS, or the residual sum. Is the each individual error, right? So what is individual error? Each error is going to be what? So it's going to, first one going to be y1 is the data point. Your predicted value is beta naught hat minus beta 1 hat times x1, right? Whole square. That's the first one, right? Plus you'll have the same thing. You'll have y2 minus beta naught hat minus beta 1 hat times x2 the whole square. And then you keep going on, and then you finally get to y1, yn minus beta naught minus beta 1 xn the whole square. This is what you try to minimize anyway, right? The residual sum of squares to obtain the lamp. So this is one measure of the error. You can always come after computing these square estimate, you could plug this in and then check what's your residual sum of squares going to be like. Very good. So now how do I understand the accuracy of this? So this, given these estimates like this that we have here in this simple setting, so we call this simple linear setting. So what I want to do is I want to assess how good this estimate is, right? Like, is it really good? Like, how to assess it? So you remember the first day in day 1. So recall, let's go. So let's write down how to assess. So the question is how to assess the accuracy of this. Like, is this really valid? So for example, if you recall on day one, in R we do 100, or we do in R we drew 100 lines, right? And then try to find the best line. So, but of course, we just did some flashy thing and said, okay, just by some idea we had this motion of best. Today, I want to spend some time trying to see when are these estimates really good? Like, when is this a correct estimate? If I give you a data set, is there a way which I can assess this? That's what we'll do in lecture 2.